As physicists, we've enthusiastically guessed this moment for over a century. Beginning around 1916, this event marks a remarkable accomplishment, offering a glimpse into one of the universe's most fascinating and puzzling phenomena: black holes. These cosmic monsters, known for their immense gravitational pull, remain incredibly elusive. While they exert a massive gravitational influence, they are nearly imperceptible to us, making them even more mysterious. One such black hole, possibly weighing between 2 to 4 million times the mass of our Sun, may be the subject of this discovery. Over the past several decades, research dedicated to black holes has transformed our understanding, taking us from a state of complete ignorance to one where we are beginning to get an intimate look at them. Now, things have taken an even more exciting turn, as physicist Michio Kaku has revealed that we have finally figured out how to look inside a black hole. This discovery opens the door to an abundance of new information that could illuminate aspects of science we may have previously overlooked. Let's take a deep dive into the realm of black holes and uncover what exists within them. While space is vast and infinite, the concept of black holes raises countless questions. Before we delve into the specifics of Kaku's astonishing findings, it is essential to understand the fundamental nature of black holes. Most people have at least a basic understanding of what black holes are, but significant gaps in our knowledge still remain. The theory of black holes dates back to 1916 when Albert Einstein published his general theory of relativity. This theory predicted the existence of black holes, though at the time, the idea was purely theoretical. It wasn't until about 50 years later, during the 1960s, that concrete evidence of their existence began to surface. Scientists studying the Cygnus constellation observed an unusually bright blue star emitting X-rays. This star, they discovered, was not stationary but was orbiting a massive dark object. Upon further investigation, it became clear that these X-rays were being drawn into this object, leading to the coining of the term black hole. This discovery was a groundbreaking turning point, confirming that black holes were not just a product of Einstein's imagination, they were real, tangible entities that existed in space. It became evident that they needed to be studied more thoroughly. Scientists from around the world began focusing their research on a particular black hole in the Cygnus constellation, designated Cygnus X1, located approximately 6,000 light-years from Earth. This black hole was several times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that not even light could escape it. This is the defining characteristic of a black hole, the ability to trap light within its gravitational grip. The concept of a black hole is both fascinating and terrifying. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape from it. Any object that ventures too close is sucked in, and once it crosses a critical boundary, it is lost forever. This inherent danger is why expanding our understanding of black holes is so crucial. After the discovery of Cygnus X1, researchers embarked on an extensive search for other black holes. Estimates now suggest that there may be more than 100 million black holes scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are incredibly difficult to detect, meaning we don't have an exact count. What is clear, though, is that there could be millions of black holes within our galaxy, highlighting their significance in astronomical research. The main concern surrounding black holes revolves around their gravity. Their gravitational force is so immense that anything that gets too close is inevitably compressed to an extreme degree until it becomes a singularity. In simple terms, black holes act as cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most unsettling aspects of black hole research is that if someone were to fall into one, they would be stretched into a long, thin form due to the tidal forces acting on them. This stretching would occur gradually, and the person would perish before reaching the final stage of this process. So, let's be clear, it's best to avoid falling into one at all costs. Even though the nearest black hole is about 500 light-years away, it still raises questions about the potential dangers they pose to us. In 2021, a remarkable milestone was achieved when scientists successfully captured the first clear image of a black hole. This particular black hole was located in the M87 galaxy. The research team took multiple images over several nights, and by stitching these images together, They created a comprehensive photograph that revealed astonishing details. It turns out that a black hole is not just a giant void of nothingness, as many people assume. In fact, a black hole consists of three distinct layers. 1. The event horizon. Once an object crosses this boundary, there is no turning back. It will inevitably be drawn into the black hole. 2. The photon sphere, a region where light itself can be trapped in orbit around the black hole. Any light entering this area becomes ensnared by the black hole's gravitational force, unable to escape. 3. The singularity, the point where everything that falls into the black hole is crushed into an infinitely small space. This is where the laws of physics as we know them completely break down, making it impossible to predict what could happen. Even more fascinating and terrifying is that no two black holes are exactly alike. While they all follow this three-layer structure, the way they function can vary dramatically from one to another. Typically, scientists rely on telescopes to observe celestial objects. However, when it comes to black holes, this method isn't practical. Since black holes are invisible, scientists study them indirectly by observing the radiation they emit, along with the surrounding gas and dust. Sending probes like Voyager to explore a black hole is not feasible, as anything crossing the event horizon would be pulled into the singularity and destroyed. Therefore, researchers must study these extraordinary objects through a two-dimensional lens, despite their inherently three-dimensional nature. One theory about the formation of black holes is that they result from collapsing stars. When a star burns through its fuel, it can no longer generate the energy needed to counteract gravity, leading to an inward collapse that can ultimately create a singularity. To further investigate the nature of black holes, NASA scientists turned their attention to the core of the M87 galaxy. Here, astronomers observed a massive whirlpool of superheated hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The sheer force of the spinning gas should have caused it to fly apart, yet it remained intact. Scientists speculated that an enormous mass at the center of the galaxy, weighing as much as 2 to 3 billion times the mass of the Sun, was holding it together. This mass could only be explained by the presence of a black hole. However, black holes may not always be formed by collapsing stars. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the dynamics of a rotating black hole. Kerr's solution showed that instead of collapsing into a single point, a rotating black hole would form a thin disk, a phenomenon known as the ergosphere. The ergosphere is a region surrounding the black hole where the laws of physics begin to break down. Kerr's solution also predicted the existence of an Einstein-Rosen bridge, commonly known as a wormhole. This hypothetical tunnel could connect two separate regions of spacetime and, according to some theories, might even link parallel universes. If someone were to fall into a black hole rather than being crushed, they could theoretically pass through this wormhole and emerge in a different universe, or even at a different point in time. How wormholes work. We should initially embrace the idea of spacetime as per Einstein's hypothesis of relativity. Reality is entwined, shaping a four-layered texture. Objects with mass twist this texture, creating a gravitational field that makes different objects push toward them. Picture spacetime as a piece of paper. If you put 2 points on it and draw a line between them, that line represents the path objects take through spacetime. However, if you could fold the paper, you'd create a shortcut between the 2 points, similar to a wormhole connecting two distant regions of spacetime. Wormholes are not just science fiction. They are a direct prediction of general relativity. However, no one has yet observed one, and they are inherently unstable, likely collapsing almost immediately. The potential for wormholes to serve as travel pathways through reality has fascinated physicists for decades. While the idea of crossing vast distances instantly or traveling through time is undeniably exciting, the challenges are immense. Einstein's theory of relativity predicts that nothing can travel faster than the speed of light, placing an absolute limit on the feasibility of wormhole travel, at least with our current understanding of physics. Recently, a particular kind of wormhole, known as the CERN wormhole after Royer, has captured the imagination of many. This theoretical wormhole would connect two distant points in spacetime, possibly even linking different universes or moments in time. Critics, however, argue that the CERN wormhole may be unstable or impossible to navigate due to extreme radiation and forces at the quantum level. Some physicists point out that Einstein's equations, used to describe black holes and wormholes, do not account for the quantum forces governing subatomic particles. To truly understand these phenomena, a new theory that unifies quantum mechanics with general relativity is required. One such approach is the theory of everything, which aims to explain how the universe functions at all scales, from the smallest particles to the largest cosmic structures. Michio Kaku, a leading theoretical physicist, has been working on this unified theory for decades. A promising candidate is superstring theory, which suggests that all fundamental particles are actually tiny vibrating strings. In this framework, the universe is viewed as a symphony, with different particles corresponding to different vibrations of these strings. Superstring theory also provides potential explanations for black holes, wormholes, and other exotic phenomena by demonstrating how strings twist the fabric of spacetime. However, despite its promise, superstring theory remains highly speculative, requiring extra dimensions of spacetime that we cannot yet directly observe. Some theorists suggest these dimensions were more prominent during the early universe, just after the Big Bang, and have since collapsed as the universe expanded and cooled. The potential of superstring theory to explain black holes, wormholes, and the fundamental structure of the universe remains one of the most exciting frontiers of modern physics. As we continue to unravel the mysteries of spacetime, black holes, and the very nature of reality, one key realization remains: we are only scratching the surface. Michio Kaku's work in string theory and the ideas surrounding quantum gravity have begun to offer potential answers. Although technological advances like the Event Horizon Telescope have allowed us to gain a clearer picture of black holes, much remains beyond our grasp. The frontier of theoretical physics, especially regarding black holes and spacetime, remains an incredibly active area of research, full of speculation and exploration. Beyond their obvious role in shaping spacetime, black holes have become central to discussions about the origins of the universe itself. String theory suggests that cosmic collisions could lead to the formation of new universes, and black holes might be essential in this process. Some theories even propose that our universe was born from the collision of two pre-existing universes, or that we may, in fact, exist inside a black hole. If this idea proves correct, it could completely overturn our understanding of the Big Bang and reshape our view of the cosmos. The possibility that black holes could serve as gateways to other universes or hold the key to time travel remains a subject of intense speculation. However, the mechanics of wormholes and our ability to navigate them remain a major mystery. Even if wormholes could form stably, the extreme radiation and gravitational forces surrounding them might make them impossible to traverse safely. Some physicists speculate that, if we could somehow stabilize a wormhole, it might theoretically allow travel through time or between distant locations in the universe. But for now, such ideas remain in the realm of science fiction, at least given our current technology and understanding. When we view black holes from the perspective of quantum mechanics, we encounter even more fascinating questions. The behavior of particles at the quantum level is fundamentally different from what we experience at macroscopic scales. In fact, the laws of physics appear to break down entirely when we consider objects like black holes. This discrepancy between quantum mechanics and general relativity is one of the biggest challenges in theoretical physics. Theories such as superstring theory offer a potential framework to reconcile these differences by introducing extra dimensions and new insights into the nature of gravity. However, this theory has yet to be experimentally verified, and many of its predictions remain untested. Theoretical physicists like Kaku are working tirelessly to unify these two great pillars of physics, quantum mechanics and general relativity, into a single theory of everything that can explain the full spectrum of physical phenomena. Such a theory would not only deepen our understanding of black holes and other exotic cosmic objects but could also shed light on the very fabric of spacetime itself. The concept of extra dimensions, as predicted by string theory, may help explain the hidden forces governing the universe. It suggests that what we perceive as four-dimensional reality may actually be just a small slice of a much larger, more complex structure. Another major area of study is the role black holes play in galaxy formation and the large-scale structure of the universe. The discovery that supermassive black holes exist at the centers of most galaxies, including our own Milky Way, raises further questions about their influence on galactic evolution. It is speculated that these black holes might regulate galaxy growth, control the rate of star formation, and even play a role in determining the universe's ultimate fate. The fact that black holes could have such a profound impact on the cosmos adds another layer of complexity to their already enigmatic nature. Additionally, the extreme radiation emitted by black holes, known as Hawking radiation after physicist Stephen Hawking, has led to fascinating debates about the fate of information that falls into a black hole. For decades, scientists have argued whether information is lost forever once it crosses a black hole's event horizon, a concept known as the information paradox. Hawking's groundbreaking work suggested that black holes could emit radiation, gradually causing them to evaporate over time and potentially resolving the paradox. However, this remains an open question, with no definitive answers yet. What is clear is that the study of black holes has not only provided profound insights into gravity, space-time, and the nature of the universe, but has also opened the door to an entirely new frontier in physics. Black holes challenge our understanding of the laws of nature and continue to provide fertile ground for groundbreaking discoveries. As our observational tools improve and we delve deeper into the quantum and relativistic realms, it is likely that we will uncover even more surprises, reshaping our view of the universe in the process.